Hello everybody, welcome to chapter 1.7, and we're going to talk about composite functions. Our goals today are to be able to add, subtract, multiply, divide functions. We're then going to find composite functions, and then we're going to talk about finding the domain of composite functions. So we're going to start off with some information. Given that f of x equals 2x minus 3 and g of x equals x squared minus 1. Here's what we can do using the properties of functions. Let me focus that a little bit better there. Okay, let me fix that for a second. Alright. Now, what we can say is that f plus g of x is the same as saying f of x plus g of x, which is the same as then saying that that's 2x minus 3 plus x squared minus 1. We can put those in parentheses. And we know from algebra we can combine like terms here, and we could get x squared plus 2x minus 4. And I want you to understand that what you would be doing here on a graph, if you were asked to add these two functions, you would be adding just their y values. If we had f minus g of x, then that's the same as saying f of x minus g of x. And that's the same then as saying 2x minus 3 minus x squared minus 1, which would get us negative x squared plus 2x minus 2. And here on the graph you would subtract the y values if you were just given some coordinates and not a function. F times g of x is the same as saying f of x times g of x, which is the same as saying 2x minus 3 times x squared minus 1. And if we were to FOIL that out and simplify everything, we would get 2x cubed minus 3x squared minus 2x plus 3. Lastly, if we had f over g of x, that's the same as saying f of x over g of x, which is the same as saying 2x minus 3 all over x squared minus 1. And it's important to understand here that the domain, separately, f of x and g of x have a domain of all real numbers, but now the domain of this f over g of x is that x is not equal to plus or minus 1. Okay, so let's make a little note of what happened there. For the f plus the g of x and the f minus the g of x, our domain was all real numbers. But then as soon as we made it a fraction, we had some values that would make the bottom 0. We had some values that would make g of x 0. So that's why f over g of x has a domain that can't include positive or negative 1, because that would make g of x equal 0. Alright, let's do another example. So say we're asked to find f over g of x and g over f of x for the functions f of x equals square root of x and g of x equals radical 4 minus x squared. F over g of x is just equal to f of x, which is square root of x, all over 4 minus x squared. And g over f of x is radical 4 minus x squared over radical x. And here we would have a domain that could include 0. We can include 0 here because then we just have to square root of 4, which is awesome. We can do that. but then we could not include 2. We can include every value between 0 and 2, but we couldn't include 2 because then we would get a 0 on the bottom of a fraction, which is not allowed. For this function, what we could not have would be 0 this time. And we still have to obey the top radical. The top radical can now be 0. We can include 0, but we can't be anything less than 0. We can't be a negative number. So we get to include 2 now. And it's interesting how these domains kind of flip-flopped, right, in the values that they could include or could not include, because this time we were worried about making g of x 0, which would be a 2. And here we were worried about making f of x 0, which would have happened if we had a 0. That's why we couldn't include 0 here, and we couldn't include 2 here. All right, I'll get a new sheet of paper. So let's talk about the composition of functions. So it looks like this. It has like a little O in the middle. It's not multiplication. It says like a fog of x, which is just saying f of g of x. Or you could say like a little goff. I know it sounds silly to say goff, but like g and like a little tiny circle f of x, which just means similarly g of f of x. Let's do an example of what this means. So we're given that f of x equals x plus 2, and that g of x equals 4 minus x squared. And first we're going to find, let's do a little bullet point over here, we're going to find f of g of x. Let me make that a circle. There we go. Little f of g of x, which really means this, which really means f of 4 minus x squared, right? We just replace g of x with its function. And now what we're going to do is we're going to take f of x. We're going to take x plus 2. We're going to write that, but instead of writing x, we're going to write what's inside here. So we're going to say 4 minus x squared plus 2. And again, I just want to highlight what happened there. We had an x. We replaced that x with 4 minus x squared because that's what was inside our parentheses up here. Okay. And now if we simplify this, we get negative x squared plus 6. If we go the other way, if we do g of f of x, that's the same as saying this, g of f of x, which is the same as saying g of f of x, which is x plus 2, which is the same as saying this exact same function, 4 minus x squared, but instead of that x, we're going to write this. So we're going to say 4 minus x plus 2, and then we have the little squared, so we write squared. Again, that's where the x plus 2 came from, right there. We just filled it in for x. And now, if you remember expanding binomials, you would know that this is the same as saying x squared plus 4x plus 4. And then if we make all of those negative, then we get 4 minus x squared minus 4x minus 4. And we can see right away that our 4's would cancel out. We'd have 4 minus 4. And so we'd get negative x squared minus 4x. And it's interesting to make a table to see what really happened here. Let's do that with f of x. Let's make some tables to see what happened with our y values, or our g of x and our f of x values. So if we add a table first of our x values and our g of x, remember we can't have g of x values without first inputting x values. Let's just go ahead and do 4. We'll do 0, 1, 2, and 3. And if we were to substitute in 0, 1, 2, and 3 into g of x, we'd get the following values: 4, 3, 0, and negative 5. And then we use those g of x values to create our f of g of x values. So the g of x values of 4, 3, 0, and negative 5 create a 6, 5, 2, and negative 3 for our f of g of x function. And then what we can kind of say here is we can kind of use these first two tables to create a third table using just x and f of g of x. X and f of g of x. And what we can say then is that substituting in 0, 1, 2, and 3 into f of g of x gets us that 6, 5, 2, and negative 3. So that's what g of x helps us do. And what we can conclude from this is that f of g of x gets its domain, its x values, from g of x. So long as those values are defined in f of g of x. And we'll do an example of what I mean by that. Oh, here we go. Sorry. Now you can see that. All right, moving on. The last thing that I have to show you, let me grab those notes real quick. Oh, goodness gracious. All right, I'm back. Sorry about that. So the last example, what I'd like to do is illustrate what I meant by talking about the domains of composite functions. So say we're asked to find f of g of x for f of x equal to x squared minus 9 and g of x equal to radical 9 minus x squared. Okay. So we would begin by writing f of g of x and noting that that just means f of g of x, which means, and another thing I'd like to just note real quick, what this means in words is that it's the function f in terms of g of x. F in terms of g of x. Let's actually write that out. Little fancy f, the function f in terms of g of x, or in terms of just g. And that's going to be useful for when you're asked to do word problems to really understand what composite functions can help you find. All right, let's continue with this. So what this is saying is f of radical 9 minus x squared, which really means we're taking f of x, x squared minus 9, but remember, instead of using x, we're going to use this entire thing. So we're not going to write x squared, we're going to write this thing, 9 minus x squared, and then we're going to write the rest of f. We have to make this whole thing squared, and then we have to subtract 9. And when we square away this radical, we just lift the radical off the expression, we get 9 minus x squared minus 9. And as we can see here, these 9s would cancel each other out. And so we're left with the new function f of g of x is equal to negative x squared. Now here's what's important for you to understand. Right now, the domain of this function is not equal to all real numbers. Let's just circle that or box that or something. we want to understand this. Normally, negative x squared would definitely include all real numbers. That's just a parabola, that U shape. It would go to infinity. But because this is in terms of g of x, we have to use g of x's domain. And if we look at g of x, we can see clearly that we can only be the numbers from -3 to +3. Anything else in here for x would make a negative number under the radical, which would be imaginary, which we couldn't have. So what the domain of this function is, of negative x squared here is actually going to be g of x's domain. So what we can say then is the domain is every value from -3 to +3. Alright, we got the domain from g of x. That is all I have to show you for this video. Thanks for watching. We'll see you in class tomorrow.